Good morning, everyone. Good morning again, and welcome to today's webinar. How can we stay within a safe operating space for water? The insights from the SOS-Water Framework. So my name is Mikael Mügge of Utima Research. We're a partner in SOS-Water, and I'll be moderating today's session, which includes a 40-minute presentation and a 20-minute interactive Q&A. So as water scarcity, pollution, and climate-driven extremes intensify, the need for actionable frameworks to guide sustainable water management has never been more urgent. The SOS-Water Project, funded by Horizon Europe, is developing a science policy approach that bridges planetary boundaries, thinking with practical tools for basin-scale decision-making. So today, our speakers are two leading voices in the field of integrated water resource management and environmental modeling. So let me first introduce Dr. Tahir Kahil. So Tahir leads the Water Security Research Group at IIASA and is a senior research scholar in the Biodiversity and Natural Resource Program. His experience spans hydroeconomic modeling, water allocation economics, and the design of policy interventions for resilience under global change. He's joined by Professor Andrea Castelletti. So Andrea is a full professor of natural resource management and environmental systems analysis and management at Politecnico di Milano, where he leads the Environmental Intelligence Lab. With over, I think, 240 publications or so and multiple prestigious awards, including the Aspen Institute Award and the Frontiers Planet Prize, Andrea is renowned for his work at the intersection of AI, decision-making under uncertainty, and sustainable water infrastructure. So today, our two speakers will present the objectives, the methods, and case studies of the SOS-Water Project, a Horizon Europe initiative that's creating a breakthrough framework to define and operationalize the safe operating space for water resources. So they will share with us in the next half hour an overview of the project, introduce the safe operating space concept, and walk us through the key components of the SOS-Water Framework. Please feel free to submit your questions in the chat throughout the presentation, and we will address them during the Q&A sessions. And I look forward to a fruitful and constructive next 45 minutes. So I think let's get to it, and I pass and hand over the stage to Tahir to kick off the process. Thank you.
Thank you, Mike. I will now share my presentation for today. Okay, I hope you can see it. So good morning, everyone. Warm welcome to this first SOS-Water webinar. My name is Tahir Kahil. I'm a researcher at IIASA, and it's my pleasure to coordinate the SOS-Water project. In my presentation today, I'll give a brief overview of the SOS-Water project, which will be then followed by a more detailed presentation of some of the results obtained in the project so far. So the SOS-Water project is a Horizon Europe project that started in October 2022 and is lasting for 4 years, ending in September 2026. The project was funded under Cluster 6, Food, Bioeconomy, Natural Resources, Agriculture, and Environment, under the call on land, ocean, and water for climate action, with the topic of improving understanding, observation, and monitoring of water resources. The scope of the call was to improve the assessment and performance of state-of-the-art integrated river basin model for assessing water availability and vulnerability in the context of climate change, to also improve the accuracy and spatial-temporal resolution of regional scale projection of climate change impact, and to develop techniques, monitoring tools, and innovative sensors for advancing the measurement and calculation of current and future water balances. In addition to developing a long-term observation framework and capacity in collaboration with the Copernicus program and other global initiatives, with the expected outcome to support decision makers in defining the safe operating space in terms of water quantity and availability. So the SOS-Water Consortium include 11 partners, with 10 partners from EU countries and 2 partners from non-EU countries. The partners in SOS-Water are equipped with different expertise, ranging from climate sciences and hydrological modeling to remote sensing and environmental sciences and economics and decision-making. Now, why safe operating space? So the concept of safe operating space for humanity was introduced 15 years ago and consists of 9 planetary boundaries associated with different Earth system processes that are critical for maintaining the stability and resilience of the Earth system in the Holocene and for humanity to pursue a long-term social and economic development. One of the 9 planetary boundary was on freshwater use. The concept also introduced the idea of planetary boundaries, which are system thresholds, and transgressing them could result in large-scale and possibly abrupt and irreversible environmental changes, encouraging, therefore, the design of management and governance strategies to avoid transgressing those thresholds or boundaries. However, despite the extensive history of the SOS-Water concept and various attempts at downscaling it, there is still a lack of documented application of the SOS-Water Framework to design basin scale management plans. Existing studies often focus on individual variables of the water systems with no holistic study incorporating all the dimensions of the water system at basin scale. However, we believe that to positively impact basin management, it is necessary to focus on how to operationalize the SOS concept in regional and local scales instead of simply downscaling it from a global scale. So the main objective of the SOS-Water project was to create the foundation for a holistic and participatory assessment framework of the safe operating space for the entire water resources system, accounting concurrently for all relevant water dimension. And here we are talking about water quantity, water quality, surface water, groundwater, non-conventional water, across multiple sectors. And we are considering agriculture, domestic, manufacturing, energy, and the environment across multiple spatial scales. So we are looking at upstream impact, downstream impact, transboundary level basins, under the influence of future changes in economy, in climate, and in technologies. So the methodology that was presented in the SOS-Water project aims to connect the water modeling tools with what we call local water values, and to then try to identify water system indicators to use monitoring processes and scenarios to finally develop the concept of the water system safe operating space. The project was was divided into 5 main work packages. As you could see here in this figure, the first work package was on engaging with stakeholders by trying to link the water modeling tools with local water values. The second work package was on advancing water system models and establish links between what we call pure water system models, so models that focus on the water system itself, and impact models, which are models that quantifies the impact of water resources availability and management on other sectors, such as agriculture, energy, biodiversity, and so on. We also have a work package that is focusing on Earth observation and remote sensing, and a work package that assesses state-of-the-art indicators and aims to build a system of meta indicators to improve water resources assessment, and a final work package which tries to integrate all the information from all the different work package to finally develop the multidimensional safe operating space consisting of policies, management, and scenarios. Of course, we have 2 other work packages on dissemination, exploitation, communication, and project management. In SOS Water, we have 4 different case studies, with one case study, which is the Danube Basin, divided into 2 sub-case studies, the Upper Danube and the Danube Delta. We have also the Juca Basin in Spain, the Rhine and Rhine-Meuse Delta, and the Mekong Delta in Vietnam. Now, over the last 3 years of the project partner focused on developing the SOS Water Assessment Framework and its application and testing in the different case studies. And here in this slide, you can see an overview of this framework, which includes 3 main stages. In the first stage, the water system is characterized using multiple indicators. For each indicator, a threshold is defined to identify its condition, whether it's safe, under increasing risk, or unsafe. Each indicator would represent certain objective or priority of sectors. In the second stage, we calculate how the system condition would evolve in the future under various climate and socioeconomic scenarios, co-developed with stakeholders, using an integrated water modeling system that again combines water resources models with impact models, models that calculate the impact of changes in water resources on other sectors such as agriculture, energy, biodiversity, and the economy. In the third and last stage of the framework, we introduce the management pathways to check whether the system condition would improve or worsen by introducing those pathways. So after applying this 3-stage assessment framework, we obtain what we called here the multidimensional safe operating space, combining indicators, pathways, and scenarios. How this can be useful for informing water management policy, it can help to design robust pathways which make the system safe for all or almost all indicators under all possible scenarios. It can also allow to conduct trade-off analysis across sectors, pathways, and scenarios. So by implementing management option, it could be that one sector can be safe while the other sector would be unsafe. So this is a kind of analysis that can be done with this framework. The third possible analysis is to identify critical tipping points at which changes in action and scenarios would result in large shifts in safety of the system. And before I end my presentation, I would like to highlight the central role that stakeholders play in the definition of the multi-dimensional safe operating space. Stakeholders first contribute to the identification of challenges, objectives, and priorities. Then they provide feedback on indicators and thresholds. And finally, they contribute to the design of future scenarios and management pathways. Thank you very much, and please feel free to reach out to us through those different means. Thank you.
Thank you very much, Tahir. We see that it's, of course, a very complex assessment framework that we're dealing with. So thanks for that very interesting presentation. I now have the privilege to hand over to Andrea, who I think will lead us through firstly the framework and then some specific applications in some of the case studies that we're dealing with in SOS Water. So floor is all yours, Andrea.
Thank you. You see my presentation correctly?
Yes, but I think you need to flip it.
Is
Now
that
we're
correct? Okay. So thank you very much. Now, what I'm going to present today is something a little bit more technical with respect to what I has now introduced, and particularly is the work we are doing trying to translate a safe operating space, I will call it SOS in my presentation, into something which is more, say, operational. So
Andrea, sorry to interrupt. I think you need to click one more button on your screen in order to continue to share.
Is it?
I think now we're good. Thank you.
Good. So I would say into a concept which is a real decision support framework for water system. So the idea is that we have a very powerful global idea, the idea of SOS framework, and we want to make it more concrete and useful for water managers, planners, and policymakers. Now, let me first setting a little bit the stage. Our water systems are increasingly under pressure from global socioeconomic drivers. You see in the figure, world population continue to grow, and this is resulting in an increase in energy demand, in food production. And the thing is that these demands directly translate into rising pressures on water resources. More people means more domestic water use, more food production means more irrigation, more energy, particularly in emerging economies, often involves hydropowers, water cooling of thermal plants. And so all these pressures are not abstract, but they somehow shape real constraints and generate conflicts in water system around the world. The second component is climate change. So we are going through a climate crisis now. This is pretty evident. So what you see moving here is the anomaly in summer temperature in the last decades. And this is a clear signal of a big planetary change. And actually, rising temperatures mean altering hydrological cycle, mean more frequent drought, more intense floods, changes in snowmelt timing, as well as a growing uncertainty in water availability in the future. And actually, water systems are at the front line of climate impact. At the same time, dually, they are also central to adaptation and resilience. So one key thing we want to understand through the SOS project is understanding how much stress a water system can absorb before it reaches a tipping point and kind of a irreversible state. Now, this brings us to the concept of planetary boundaries, which was introduced in 2009 by Rockstrom and colleagues. I guess the idea is a brilliant idea. So it's the idea that Earth has limits, boundaries, by the way, and we should not cross them if we want to keep our planet into a stable and resilient state. Of course, these boundaries are multidimensional, so they pertain to different type of aspects, climate change, biosphere integrity, biogeochemical flow, and of course, there is also one dimension that you can see here, which is freshwater. Now, safe operating space is the area within this boundary, so it's where we can operate safely by the point of view of society, economics, and the environment. So we all think and agree that the framework is quite powerful because it's a way of somehow providing a concept of sustainability and resilience in a quite, straightforward way. At the same time, this type of framework is a very global and at the same time little abstract type of framework. And so in time, since the introduction in 2009, there were many attempts to add component to the framework, trying to make it, if you want, a little bit more operational and practically usable. And so you see e-flow component, then the groundwater component. Someone added the green water component because the original one was only focusing on fresh water. And so a number of refinements have been proposed in time, but we argue that despite these improvements, still this idea of global boundary is quite difficult to apply in practice at the local scale. It's like it tells us we are in trouble. So I don't know, a red signal on the freshwater dimension says you are in trouble in the water domain, but it's not telling us where we are in trouble in the earth, why we are in trouble, and especially what we should do to get out of this trouble. So we try in this project, what we try to do was exactly make an effort to bridge this gap between a nice and very, say, powerful global concept into something locally valuable and usable, say. And particularly what we identify as main shortcoming of this global framework to be, used, or if you want, downscale on the local scale, are these 4 points. The first one is about the complexity of many water systems, which include a number of stakeholders and actors, and as a consequence, a number of water values. And so is a multi-sector, multi-actor, multi-objective problem that we should somehow try to consider. The second one is that the framework, the original one, focuses on water quantity, while the number of other aspects are related to biodiversity, water quality, and also governance, which are somehow neglected by the framework. The third point is that the framework is capturing like a snapshot. So it's telling you, okay, you are in trouble. When? Now. And what about the future? So what we try to do in the project is to see how this framework may evolve in the future. And now this evolution is somehow influenced by external drivers, so exogenous condition and endogenous action that you can take locally to adapt to changing conditions. And the last point is exactly maybe the most important one, which is how to translate this framework into guidelines or specific information and instruction you want to transfer and hand over to operators and decision makers. So this is where the SOS project that Taher has very comprehensively introduced come into play. So the idea is basically want to move from global concept to a very local and practical and usable idea. And of course, the starting point at the very beginning when we shape and draft the proposal was pretty clear to everyone. So this can only be done as long as we are able to integrate a number of different type of knowledge. Hydrology, of course, climate science, but also system theory and modeling, social sciences, ecology, and so on. So that's one of the things that characterizes this project, a strong multidisciplinarity. Second thing is that we've been, say, exploring different climate hotspots, so different situation by the point of view, of course, of the hydroclimatology, but also by the point of view of the type of stakeholders, socioeconomic issues, and governance type of structure. And so we have 4 European hotspots, and then we have the Mekong, which is an international case study that is somehow incorporating a number of different features which are common to the European project. Now, let me explain you a little bit in detail how this framework works. The idea is the one that you see on this plot. And I would say that if you consider this component of the plot, the one on the left, that's nothing new. This is a traditional integrated water resource management framework where you have actually a number of actions that you want to assess, a number of indicators that you are using as a matrix to say whether an action is good or not, is satisfactory or not by the point of view of the stakeholders. And then you have a model which is mapping action into indicators. So it's creating a sort of, in vitro condition for experiment, because of course we cannot do experiment in real life. So we do them in a digital twin of the real world. And of course, what we are building is a sort of, metrics where the different action are generating different value of the indicators. And of course, then there is another component, which is, are we doing this for the historical observation? Are we considering future scenarios? How do we build these future scenarios? So what is making these scenarios relevant for our problem? So climate, socio-economic scenario, technological scenarios. And so this is adding a dimension to our problem, which is same indicator, same action, but in different future scenarios. How this impact of this action on specific indicators, so on a specific sector, is evolving across time. And of course, a key element is the participation of stakeholders, as Tara mentioned before, which is actually permeating the whole framework. But this is nothing new, I would say, under the sun. This is, for those of you who have experience of integrated water resource management, this is the typical EWRM framework. What we are changing is adding this new component, which is the idea of threshold. So it's the idea inherited from the SOS framework that we want to use and define boundaries. So we want to understand whether the value of this indicator are indicating a situation which is good, safe, and probably across the scenario lasting in this positive and optimistic condition for times, or whether we are in a condition like orange, which is, a delicate transitioning situation from a safe to an unsafe condition, or whether we are in a red, high risk condition. So somehow we already cross the boundary and we are totally outside the safe operating space. So that's the thing we are adding to the framework. And so the idea is basically see how a given pathway, so a given adaptation measure that you may implement locally can bring you from a condition, for example, like this one, which is on the boundary of the safe operating space and is bringing you back into the safe operating space, or vice versa, starting from a positive condition, you may evolve into a negative, risky situation. So that's the type of thing we want to do. And this type of analysis is something we want to do locally, where the global component is somehow included in this scenario, because of course this scenario are considering all the climate policy that may be implemented, which are resulting, of course, in different climate scenarios or different socioeconomic pathways, or also in different type of technological advancements. So that may be different efficiency in energy system, or a different cost of producing fresh water, and so on and so forth. Now, let's explore the way we want to use this framework stage by stage. The first one is actually the baseline. So this kind of a vector of cell is telling you that the different sectors that we are considering, for example, fish, hydropower, sediment connectivity, and so on, are in different condition measured by different, say, values of the color blue. And then, of course, there's the problem of interacting with the stakeholders to try to understand how they judge whether an action is good or not, and then build these hierarchies of indicators through a participatory approach, where we've been doing very, say, intense work of interaction with the stakeholders to elicit their preference and construct the way they judge whether an action is good or not for them. Then, of course, you want to put some threshold and understand whether the status quo, the baseline, is in a good, safe, or transitioning or unsafe condition. I will go back to the threshold definition later, but this is a tricky point, technically speaking. And then, of course, we want to understand what happens if, without doing nothing, so just, evolving the present situation into the future, just, being affected by exogenous drivers represented by scenarios of climate, economic change, technological change, the safe operator space will change. And so you can see that the different layers in this direction are different scenarios. Of course, to do this type of analysis, we need a model. So we need a model which is somehow simulating how the present condition will evolve in the future under different type of future scenarios. The third stage is when we say, okay, now we know that things can get worse. In some cases we are lucky and things may improve, but generally we notice that there is a worsening of the situation. We want to act. So we want to adapt locally to this ongoing global change. And so we identify again with stakeholders a number of local pathway, and we see how this pathway may make your indicators changing in values in the future. And again, through the threshold, examining whether these changes will move a given sector across thresholds. So in the positive direction of getting back into the safe operating space or pushing the sector outside the safe operating space. Now, I want to give you, in what remaining of my presentation, an overview of what is behind all this step in these stages, because there is a lot of technical and methodological aspect that we are exploring and experimenting. Some of them are consolidated knowledge, some others are new ideas that we are developing. So the first point is, of course, identifying indicators. This is nothing new under the sun. I mean, many of us have experience of participatory approaches to identify through bottom-up process indicators, be the hierarchies of criteria and then appending indicators to this hierarchy. Of course, on top of traditional indicators, we also try to include new concepts like equity, transgenerational justice, climate justice, sustainability, flexibility. So there's a kind of a combination of bottom-up indicators and standard indicators that we consider somehow, let's say, they are not necessarily represented by a group of stakeholders now, but they may be represented by stakeholders in the future. Then we need to fix a threshold in these indicators. So we need to understand whether the value of an indicator is good, how far it is from a critical threshold, and whether the criticality, so the threshold is just a value or is an interval of value or is a gradient of values. And here again, that's more on the research side. We are exploring different type of approach. Of course, we start from what you can find in the literature as a baseline. And then we are trying, when feasible and available, to really downscale boundary defined at the global level at the local level. And then we have also a couple of other approach. One is interaction with the stakeholders, and then one is try to look into the way changing the value of indicators control response change to see whether there are discontinuity points which may represent threshold. And then again, the key issue is how do we define boundaries? So are boundaries just one threshold value, or are a continuum of changing values that bring you from a safe area into a totally unsafe area through a number of intermediate steps? And then we have future scenarios. Here we are using a sort of hybrid approach. So we use traditional top-down approach where you have, global model, GCM, and then you do downscaling, for example, making the example of climate scenario down to the local dimension. But at the same time, we are also building with stakeholders narratives of scenarios starting from what they consider to be a challenge, potential perturbation to the status quo in the system. So we mix up these two types of approach. And then there's a problem of identifying adaptation measure. And again, is a heavily a participatory type of approach. We're doing a lot of work with stakeholders because, of course, there are a number of actions that you can consider are, say, common to many watershed in the world, but there are very localized actions that they may emerge from the type of system we are dealing with locally, and then suggest adaptation which are really, really matching the characteristic of the system at hand. And this is one of the key points that we that somehow push up the interest in doing this downscaling of the framework, because we realize that there is a lot of biodiversity, cultural and social biodiversity, as well as ecosystem biodiversity in the different watershed in the world, and these make the use of a global framework highly valuable at the local scale. That's why we are looking at this sort of operationalization of the safe operating framework. And then a couple of more information. Again, methodologically, a key point we are exploring is how uncertainty stemming from different type of sources. So there's traditional epistemic uncertainty, uncertainty in scenario design, uncertainty in the way you define pathway, and the potential gap between the definition of a pathway and how the pathway will look like once it is implemented. And then uncertainty in the way you define threshold, or how all these sources of uncertainty are propagating through the framework and eventually impacting the representation of this sort of hypercube representing for us the safe operating space. I think I use all my time. I had just want to give you very quickly an overview of one of the more challenging case study we are dealing with. I would say they are all challenging. This is more challenging because of the size, even if Danube and Rhinas are very big case study. And because probably with respect to Europe, in Southeast Asia, as well as in many places in the global South, there's still a lot of investment going on. So there is a lot of, dynamics in the way adaptation measure can be interpreted. There's a lot of investment in the Mekong, the idea of building a lot of new dams, more than 120 dams, with the idea of supporting local production of energy, growing interest in expanding irrigation schemes, flood control as well. But of course, there are drawbacks because dam are, as a first type of impact, fragmenting a river system, and so interrupting a number of fluxes from the source, from the spring to the sea. And so we apply our framework. So we identify a number of indicators pertaining hydropower production, but also sediment flow, production of greenhouse gas emission by impounded water, fish catch, changes in hydrological flow, and then the agricultural water demand along the river. Been considering a number of scenarios, and I'm going very quickly through these preliminary results. So we're building, the future evolution of the system by the point of view of the drivers. And then, of course, we are running a model which is somehow taking all these scenarios, all the local pathway that we are considering, and simulating what will happen if a given scenario happen and is combined with a number of local pathway. This is my last slide, actually. You see the type of pathway that we are considering. We consider a subset of the new dam that are planned to be constructed in the next 25 years. We are considering intervention to mitigate the impact of dam by changing the way sediment are managed through flushing, sluicing, depending on the type of dam. We are considering a reservoir-specific water management strategy, because we realize that even if to a small extent, changes in operation of reservoir are also impacting sediment transport. And then we're looking at the agricultural expansion, the introduction of measure to re-establish connectivity for fishes, and so on and so forth. So these are very preliminary results. So this is what we have so far, but it's just to give you a sense, more practical sense of how this safe operating system may look in a real world case study. And I would say with that, I'm done. Thank you for your attention. I hand it over back to Mike for the moderation.
Thank you very much, Andrea, for such an interesting and insightful and actually thought-provoking presentation. So in the meantime, we've received a number of questions, so thank you very much from the audience. And I'll be tag teaming with Silvia to try to answer as many as we can in the next 17 or 18 minutes or so. So perhaps, Silvia, I can ask you to pose the first questions to our speakers.
So the first question is from Sushri Spine, probably for Taher. She's curious to know about how future anthropogenic activities such as land use, land cover change, or any man-made changes in river basin are being taken care of.
Yes, yeah, thank you very much for the question. As it was shown in the framework, there is the so-called socio-economic climate change scenarios, which are used to force the integrated water system model. And in these scenarios, we follow up both top-down and a bottom-up approach. We take the future climate change and socioeconomic projection represented, for instance, by the RCPs and SSPs, but we are also co-developing with stakeholders and stakeholder workshops also how they can see the future in their case study by, for example, defining changes in land use, expansion of irrigation, introduction of new crops, or changing the crop mix. So those are part of the scenario design, and they are included into the models. Plus, we have the management pathways, which could also include adaptation to changing water, for example, water condition by introducing drought-resistant crops or introducing more efficient irrigation systems or better management of land, so that all these changes that could happen in the future are included part of the scenarios that are used to force the modeling system to then calculate the indicator. If you remember, we have this multi-dimensional space that includes scenarios, pathways, and indicators. That's it. Thank you.
Thank you. Then I have another question here. This, I think, maybe for Andrea. Given the increasing competition for water amongst various sectors, how does the SOS-Water Framework account for these trade-offs between economic development and environmental sustainability? So economic development versus environmental sustainability.
Yeah, the idea of the framework is to use what is called an ex post decision-making approach. So we basically are using a multi-objective framework where the existing trade-off, so the existing conflict or synergies between objectives are all explored. So the idea is that this sort of matrix and hypercube that you saw is a sort of discretized and tabular representation of a Pareto front, where you can see, okay, if I move this indicator of one values and this sector get an improvement of one value, how much is another sector losing or winning? So our idea is to fully explore and fully exploit a multi-objective approach exactly to make the trade-off across sectors explicit and so something you can navigate through and explore.
Thank you. Silva, do we have another question from the audience?
Yes, I have two questions from Mikkel, one to Taher, one to Andrea. The one to Taher is asking how the SOS-Water of the Upper Danube and the Danube Delta relate, probably refer to the figures where we have these two case studies indicated as separate. And the one for Andrea is asking between the hookah and Rhine case studies, if agri-production declines, how does this impact the scenarios in the Rhine as the total food requirements needs to be still met?
Yeah. Okay, I could start maybe with the first question. Thank you for the question. So for the Danube Basin specifically, we are developing the model for the whole Danube Basin. We are developing a basin level model at high spatial resolution, which is 10 by 10 kilometer grid resolution. So the whole basin is connected from upstream to downstream. Now for the SOS-Water project, we are focusing on certain sub-basins within the whole Danube Basin. Although we are running the whole Danube Basin, we will be presenting results of the safe operating space for this kind of sub-basin level within this upstream and downstream part, because of the different climatic condition, of the different challenges faced in the different parts of the basin. But the model that we are developing within the SOS-Water is a model for the whole Danube Basin at a high spatial resolution. Thanks. I hope this responds to the question.
Yeah, Celia, can you kindly repeat the question, because I just heard it was about the Rhine and the Yucca, but I missed part of the question. Sorry for that.
Yeah, it was about if agri-production or other type of farming declines, how does this impact the scenarios in the Rhine? Because the total food requirements need to be met.
Yeah, I should say that honestly, I don't know how to reply to this question, because I don't feel
Yeah.
even yet to this point in developing scenarios and modeling the Rhines. But the idea, of course, is to be able to capture, as long as we do have this information, all these type of changes. So the idea is to try to capture every type of change occurring in the basin in the future, and say the key point is sort of distinction between adaptation that we mostly consider to happen locally, and mitigation that in our framework is, I would say, 90% included as an exogenous driver in the scenarios.
And thank you very much, Andrea. I've got here, I think, probably for Tahir. It's all about comparing the SOS-Water Framework from previous integrated management or water management models. So basically, how does the SOS framework differ from previously integrated water management models, and what do you see as the most significant breakthrough that will enable its uptake by policymakers? So here the question is around policymakers. Tahir?
Yeah, thanks, Mike, for the question. A bit complicated question, but I would say that I think Andrea responded to the question during his presentation. But from my point of view, the SOS Water Assessment Framework, first of all, it is a framework that is consistent with the global assessment. So at the global level, this SOS Water Planetary Boundary Framework is being used to assess how globally how the environmental sustainability is being maintained, and we are developing a framework that is consistent with this global narrative. Then we are including multiple dimensions of water resources and explicitly representing the water values. So that's food production, biodiversity, water supply, energy production, recreation, and all those are represented by indicators and meta indicators, which are co-identified with stakeholders. It is a flexible framework so that it can be applied anywhere in any basin by also easily adjusting the component of the framework. It is not model dependent, so you don't have to use the models that we are using in the project in the different case studies. So the framework can be applied in other case studies with other models, but still be consistent. And also the idea of introducing thresholds, and then you see how this uncertainty and thresholds and scenarios is being introduced. I think these integrated water resources management models of framework, they were quite deterministic, not considering uncertainty in thresholds and in scenarios. So we are really introducing a more comprehensive way of thinking about the water system. And to inform policy decision-making, I also highlighted in my presentation, there are different ways. Once we identify this multi-dimensional safe operating space, there are different ways to support decision-making. First way is to identify robust management pathways. So those are management pathways that will ensure system safety under a range of conditions. Second thing is to conduct trade-off analysis, also what Andreas mentioned. Through multi-objective analysis, you can see what would happen in one sector compared to another sector if you do a certain action. And then finally, to also help to identify tipping points. So when major shifts in the system safety will take place if certain action or scenarios happens. So that's how it could inform decision making. Thank you.
Thank you very much. Great answer to a very complex question. Silvia, we got some more questions coming in?
We do. So maybe one bit quicker. Albert is asking if we account for virtual water flows in the physical water assessment of the SOS-Water Framework. Maybe for Andrea.
Yes, sorry, I probably have a connection problem, so I didn't get your question, Silvia.
If we account for virtual water flows also in the modeling, in the physical assessment of the SOS.
Virtual water flow.
Virtual, yes.
No, not really, not now. Exactly because at this stage we're mostly looking at local adaptation pathway, and somehow as a consequence the indicator are reflecting these local dimensions. So we're not yet considering fluxes, and these is about both virtual water say flow and so trades and water trades, but also related to food and energy fluxes. At this stage, we are still working in a context which is considering the local dimension, and then everything else is a boundary condition impacting the local dimension. But so far, we're not be considering the other directions from the local to the global, or from the local to outside the local dimension. But of course, that's something we can easily accommodate in the framework.
And then I have several questions on the stakeholder engagement to clarify how the difference, how diverse is the stakeholder groups that we are considering, how we manage this diversity in terms of different point of views and their and indicator importance and threshold. And yeah, in general, and also how we handle uncertainty. If we evaluate also uncertainty, how much water managers and local stakeholders are willing to handle uncertainty. And yes, in general, a bit of clarification on how the stakeholder engagement is taken into account in the scenarios design and the SOS.
Okay. Yeah, maybe I respond to the stakeholders, and Andrea can address the uncertainty. That's an important topic. So in terms of stakeholders, so water resources and river basin are usually used by several sectors and users with often different objectives and contrasting interests, which could create conflicts, of course, and tension, especially in transboundary basins and with intensifying climate change impacts. And there are also complex interaction and feedback loops within the water system, and therefore engaging stakeholders is really necessary and mandatory in this type of analysis. And given that we are also talking about this multi-dimensional space and multi-objective, So different stakeholders are being involved systematically in the project, in the different case studies actually. So we have always representatives of water management and planning authorities, whether river basin organization or ministries. We have also representative of major water use sectors, that's agriculture, energy. We have also NGOs representing the environment. So we have been able to work together with major and key stakeholders in the different case study to represent actually their objectives and priorities, to identify the sectoral challenges, but also to identify those thresholds, because the sectors, they know what are the thresholds for them. So I have to say that it is very, very important to include stakeholders, not an easy task, but we have a good methodology, and I would actually recommend to look at some of our deliverables on stakeholder engagement, which are available on the project website, with I think a very innovative methodology led by our colleagues from NIVA on engaging stakeholders. Thank you.
Andrea, something to add to that, because we're running out of time, and I've got one final question that I want to pose to both of you.
No, I would say the question on uncertainty stakeholder is a key, and more general decision maker is a key one. I would say that the SOS framework is considering uncertainty so far really at the scientific level only. So we still need to understand how this uncertainty through the many sources to the output is impacting the safe operating space. So I would say we don't have in the project yet consider a very challenging aspect, which is the communication of uncertainty and how to transfer information about the uncertainty to the final decision makers.
Great. So we're just spot on time. I have one question I want to pose to both of you, just to kind of wrap it all up. And please be very short in the answer if you can. So it's really about looking ahead and looking at what is the biggest challenge in scaling our SOS framework beyond the pilot basins. So what's the biggest challenge ahead for scaling this up? Easy question, short answer.
Well, go first very quickly. Well, one of the things which was the big suspect that inspired our project is that there is a lot of diversity across the different case studies. So the idea of moving from a global framework to something locally was a good idea. At the same time, and it's justified with what we're finding locally. So big variety, a number of things that are totally, hidden if you look at the global scale. And this is at the same time a challenge, because it basically means that the framework itself can be probably exported and used in other contexts, but there's still quite a lot of work to be done to populate the framework in the different case study. And so I would say there's a 1% of common knowledge that can be transferred, but there is still need of triggering participatory process and say elicit local information and knowledge to populate this framework, which is a good thing in my opinion, because it's actually reflecting the human diversity and natural diversity and the effort to not overlooking this complexity.
Excellent. Tahir, a sentence to add to that?
Yeah, a sentence, just a quick sentence. So basically, despite how good or performant at the model we are using in our project, or even in other projects, I think the lack of data, and especially on human water management, is really a challenge. So it doesn't help us to calibrate and validate our models. It is difficult to obtain information on water use, on how infrastructure being operated, and even if the data is available, is often not accessible. So I believe this would be also one of the conclusion and recommendation we provide to the stakeholders and to the European Commission on data availability on human water management. Thank you.
Great. Well, thank you very much, Andrea, and thank you very much, Tahir, and for such an insightful and thought-provoking presentation and dialogue. And thank you very much, Sylvia, for hosting and assisting here. And of course, to everyone who joined us, thank you very much for your active participation in all this and excellent questions. So I hope you found this session valuable and inspiring for your own work, and it's been inspiring for us. We learn by engaging, so the stakeholders are a very important factor in all our work that we do. So if you'd like to learn more, because this is the first one of a number of webinar sessions, please visit the SOS Water website, follow us on social media, stay updated. There's a number of upcoming publications, tools, future events. And so basically with this, on behalf of the whole SOS Water team and all our speakers, thank you again for joining and being here, and we all wish you a great day. Thank you.